Okay, well, welcome everybody to the 10th SoFiE Seminar. I'm Andrew Patton, and I'm very happy today to be hosting a special edition of the Society for Financial Econometrics Seminar Series. Today we're having presentations from four job market candidates working in topics broadly related to financial econometrics. Our four speakers today will be Gianluca De Nard from University of Zurich, Philippe Goulet-Coulomb from University of Pennsylvania, Ha-Yoon Jung from New York University, and Merrick Lee from University of Cambridge. I think the four topics are all very different and all very interesting. I think it's going to be a great portfolio of presentations today. And so let me change my background and we'll get started with the first presenter. So let me do a quick change here. Our first presenter today is Gianluca De Nard from the University of Zurich. Gianluca, if you'd like to unmute and share your screen, you can begin.
So, thank you very much, Andrew. I'm happy to be here and present my latest work on large dynamic covariance matrices at the special seminar. Actually, it is a co-authored work together with Rob Engel, who I have been visiting for over a year now at NYU, and the usual suspects from the University of Zurich, Olivier Ledois and Michael Wolf, where I am finishing right now my PhD. So let's go directly to the background and aim of the paper. We are basically interested in estimating large dynamic covariance matrices, in particular for asset returns. And as you know, there are many important applications in finance to this end, for example, in risk management or in portfolio selection. But I want to emphasize here really on large covariance matrices. By large, we don't mean just a few dozens, but really hundreds or even thousands of assets. And that is from a computational point of view and also from a statistical point of view quite challenging. Luckily, my co-authors and I have proposed some solutions already to this end. So you're probably all familiar with this DCC model of Engel. That's a multivariate GARCH model that can really capture the conditional heteroscedasticity one observes, at least for daily financial asset returns. However, it has one main drawback, and that is that it doesn't really perform well for larger dimensions, and we want to really focus on this challenging scenario here. But there are some remedies for that. One could combine DCC, a time series model, with nonlinear shrinkage from Ledois and Wolf. That's a cross-sectional approach that makes this estimator also feasible for larger dimensions. And now the aim of this paper is to improve upon DCC and DCCNL by trying to introduce intraday data in this framework, okay? And we then use this hopefully improved covariance matrix estimator for some portfolio selection exercises. So the idea, how can we improve upon the basic model we had right now, DCC and DCCNL? The idea is that we want to come up with a less noisy volatility proxy derived from this intraday data and go even a step further and use this intraday data to derive something we call a regularized return and work with this regularized return instead of the actual observed returns. So let me say a little bit more on the estimation of large dynamic covariance matrices. So we take the DCC as a benchmark, as already said, and you're all familiar with that. The first step would be to just estimate the univariate volatilities, for example, by a GARCH 1-1 process. So you're familiar with this equation here, and we take as an innovation the residual, the returns. So R for us is a return of an asset I at time period t-1, where I goes from 1 to n. So n is nothing else than the investment universe, and this one should be a large number, and t grows from 1 to capital T, where t is nothing else than the sample size. We then use or need these conditional volatilities here for deriving this S. The S is nothing else than the devolatilized returns. That means we have to divide their actual return divide by the conditional standard deviation to have here a proper matrix with S. And additionally, we need this correlation target here, C, that's nothing else than the unconditional correlation matrix to get here to the second step of DCCNL, the estimation of a correlation, a conditional correlation matrix. However, Until now, we have only a pseudo conditional correlation matrix, which has not proper ones on the diagonal. That means we have to do this operation here to have a proper correlation matrix. But as we are interested in estimating large dynamic covariance matrices, here denoted in red, we have to pre and post multiply the conditional correlation matrix by a diagonal matrix D that contains these conditional standard deviations. So this will be our benchmark model when using here the sample correlation matrix for correlation targeting, that would be DCC. However, that breaks down at least for larger dimensions. So we are promoting to use this DCCNL estimator of Engel, Ledoux, and Wolf that uses here nonlinear shrinkage for correlation targeting. So now the question we ask ourselves is, can we enhance this DCC and DCCNL model with intraday data? We have two approaches to this end. The first one would be to come up with something we call a volatility proxy. So we want to improve upon the first step of estimating a DCC or DCCNL model. Already Molnar has used that, but only for modeling univariate GARCH model. So he says we should replace the squared returns with a less noisy volatility proxy. So this would be here the red quantity. The question is, of course, what is a good, less noisy volatility proxy? And we are trying to do that by looking at intraday data. So at OHLC, where O is the observed opening price, high is the observed highest price transacted, L the lowest price transacted, and C as usual, the observed closing price. Okay, and if we found a better volatility proxy, we then call the resulting model ID DCCNL, where ID stands for the volatility proxy based on this intraday data OHLC. Of course, then everything comes down to find a better volatility proxy. There's an entire literature on how to estimate conditional variances, and we think that for our purpose, at least, this OHLC volatility proxy is the best one, because it takes into account overnight jumps and intraday variance. So we basically use the range-based estimator of Gorman and Klaas that takes into account both. Here, just to give you an intuition what it does, here you would see the overnight jumps that looks at the range between the opening price of a day and the closing price of the previous day, but it also takes into account the intraday variance measured by the range between the highest transacted price and the lowest transacted price. Now, if you're combining that to quantities that are a standalone volatility proxy in a smart way, there are some papers who show how to come up with good scaling factors here, A3 and F. You found a much more efficient volatility proxy than just using these squared returns. And just to point out, Molnar has, at least for his univariate GARCH model, only looked at this high minus low range based estimator, basically only on this quantity here. And we think, and also empirically find, that this is suboptimal. So now to show you, or at least give you an intuition why our model works, is in here in red, you would see the volatility proxy, in blue, the absolute value of the observed return. And you see that indeed we have found a volatility proxy that is much more stable. So we really have a less noisy volatility proxy here. And by construction, it never gets zero, or not very, very close to zero. So it's indeed much more stable, but still the volatility proxy is highly correlated with this more naive observed return proxy. Okay, but please don't stop here. What we have done until now is just trying to improve upon the estimation on the diagonal of a covariance matrix. We have only focused on the estimation of conditional variances. However, in larger dimensions, you know, there are much more off-diagonal values, much more conditional covariances. So we are trying now to use that intraday data to improve also up on the second step of the DCCNL model, and that is estimating conditional covariances. The question, of course, is then how can we do that? We come up with something we call regularized returns that are derived from, again, this intraday data, or more specifically from this improved volatility proxy. Now, let me sketch the idea like that. What the standard literature is saying is that you should use the squared return as a volatility proxy in the first step, or in a univariate GARCH model. That would be the naive implementation looking from closing price to closing price. Now the literature has found some better volatility proxy, and we especially promote this OHLC volatility proxy. But please don't stop here, because not only volatilities are very noisy, stocks returns are even much more noisy, right? It's very hard to predict the stock return, so why not use the volatility proxy to go back and find also a less noisy return proxy here in red with the tilde. And we then use this return proxy as a new underlying time series in a DCC or DCCNL model and call the resulting model IDR DCCNL. Of course, then the question is, how should we go from the volatility proxy to the return proxy? The most naive way to do that would be to just set them equal, like the standard model would do. As I was saying, the return proxy is equal to the volatility proxy, but by construction, the volatility is bounded by 0. And of course, we want to have also negative returns, right? That means we have to take into account at least the sign of the actual observed return. So the naive implementation would be that the return proxy corresponds to the volatility proxy, or the square root of the volatility proxy times the sign of the actual observed return. And believe me, already this naive implementation works very good in practice and gives us a significant improvement over the traditional DCC and DCCNL model. However, we didn't stop there. We found something that works even better in practice, and that is if you use a smooth sine function. For example, here, this scaled hyperbolic tangent function with scaling factor kappa. So this smooth sine function does nothing else than shrinking the volatility proxy towards 0. So why do we need this kind of shrinking of the volatility proxy? We need that, again, because there are some scenarios or some particular cases where the volatility proxy is very stable on a certain level, but the actual observed return is very, very close to 1, okay? And for these particular cases, we want to shrink the volatility proxy towards 0 with a suitable choice of kappa. Of course, now it is very important to find here a good scaling factor. We run an extensive empirical analysis to analyze that, and I don't have time to go through that into detail during this next few minutes, but I want to give you at least the intuition how you can determine the value of kappa. So here you see the scaled hyperbolic tangent function. In light blue, we would have a kappa equal to infinity. That would be basically the sine function. That's not smooth at all. You see, it takes the value 1, -1, or 0, depending on the actual observed return. But now we want to shrink the volatility proxy for very, very tiny observed returns. So let's say we are moving around here somewhere between maybe 5 basis points and minus 5 basis points. And that would be basically the green curve of a kappa equal to 100. That means to have the shrinkage we want, we really need a kappa that is very high, probably not infinity, but it should be a number somewhere around 100. Okay, just to give you the intuition how we select the kappa. Now we use this return proxy as a new underlying time series in a DCC and DCCNL framework, and I want to show you now the results we get in an empirical analysis. So we compare these 6 estimators. DCC and DCCNL would be our benchmarks, and we are trying to use the intraday-based volatility proxy denoted by ID, or the regularized returns as a new underlying time series in this framework as IDR for DCC models and DCCNL models. So how can we test that? How can we measure the performance of a covariance matrix estimator in an empirical analysis? We do that by estimating the global minimum variance portfolio. Why the global minimum variance portfolio? Because its estimation depends only on the estimation of the covariance matrix. That means the better the covariance matrix estimator, the better must be the global minimum variance estimator. And we can measure that easily by looking at the out of sample standard deviation. That means the lower the out of sample standard deviation, the better is the global minimum variance portfolio, the better must be our covariance matrix estimator. So here is basically the most important table of our paper summarized. I plot here the standard deviation annualized for all the 6 models for the investigated investment universes 100, 500, 1000 for this particular time. So we restricted our attention from 98 to 2018 because for this time period we have really good or proper data on opening or accurate intraday data. So the first thing you should see is that DCCNL models outperform the DCC version. So that means nonlinear shrinkage really kicks in these larger dimensions, but that comes as no surprise. That was already known before, but it also works for these intraday models. What is a new finding is that if you extend the DCC and DCCNL with this intraday framework I explained before, we really get lower standard deviation, okay, in every analyzed scenario. And this outperformance from, for example, ID DCCNL over DCCNL is not only large, it's also statistically significant on a very high level. That means you have to upgrade from DCCNL to ID DCCNL by looking at this better volatility proxy, but don't stop there. The ID or DCCNL model is even better. It's in every scenario the best performing model, as it also improves upon the estimation of conditional covariances. So that is the model that we really propose. You should use that or update to that. That means you should run a DCC model together with nonlinear shrinkage, especially in these larger dimensions, but not on the actual observed return. Use the regularized returns that are derived from this improved volatility proxy. We also have some nice side effects that the intraday models can also lower the turnover and leverage. So that means for a real life application, we can also successfully reduce turnover and leverage that makes more stable and less extreme portfolios. So let me conclude. We have found that intraday data indeed lead to improved forecasting of dynamic covariance matrices in this DCC and DCCNL framework, and the results are very, very robust. So we run several sensitivity checks. Maybe I have a little bit time at the end to go through that. And we found that also for sub-periods and for other portfolios and other kappa values, the intraday models always perform or outperform the traditional benchmark only based on daily data. That means we have some clear recommendations. You should use the less noisy volatility proxy based on OHLC instead of the squared returns, because that gives you a better estimation of the conditional variances. But don't stop there. We can also improve upon the estimation of conditional covariances by coming up with something we call the regularized returns derived from this improved volatility proxy in conjunction with a smoothed sine function. So that is basically the main idea of our paper and the main results summarized in this short 17 minutes. If you have any questions, I'm happy to answer them. And if not, I maybe have another minute to go through some robustness checks.
I'm sure we're going to have questions. So let me, I should have said at the beginning that people, if they have questions, to use the Q&A button, or now at this point, raising your hand is probably the best way to go. Maybe I can ask a question to start with. I was curious whether you had experimented at all with using the open-close data to get better proxies for the covariance as well.
You mean, so using directly? No, we didn't. We didn't do that. So we only really focused on using this data to get an improved conditional variance estimator, and wanted to address the improved estimation of conditional covariances via this return proxy derived from this volatility proxy. So no, we didn't do that directly.
Yeah, okay.
That would be another possible solution. You're right.
Yeah, I mean, I can understand wanting to exploit only the high-low open-close, because you can go back further in time. You can look at a broader cross-section of stocks. Yeah. Yeah,
that's a good idea. Yeah, we can look into that. That's a good point.
I see a question from Kevin Shepherd, so I'll ask him to.
Yep.
Kevin, you can go ahead.
Hi, can you hear? I hope you can hear me. Looks like you can hear me. So, sorry. When you modify the volatility, obviously that then, even though you use the sort of same correlation estimation strategy, clearly that changes your correlations. Have you found a way to sort of think about how you would decompose the gains that you're getting, say the first order gains from just having better volatility, say forecasts from having different correlations, or are they better correlations? So my intuition on this, a simple way to try to do it, which is never perfect, is to do some sort of mixing and matching, where you take a correlation from one model and a volatility from another model, and you sort of crisscross it to see if there's anything any sort of patterns you see there, but I don't know if you have a better way to sort of do that.
No, we haven't really analyzed that in this way, but we focused on if the using this regularized return gives us some bias with this covariances or correlation, and really found that looking at this open, high, low, close data, it doesn't really introduce a systematic bias. But we didn't really check it like you have proposed. No, we haven't done that, at least not yet.
Okay, and we have one more question, which is in the Q&A. It's an anonymous, so I'm just going to read it out. The question reads, in your out-of-sample performance, you report standard deviation of close to close. How does it break down into the overnight and the intraday return?
We did this as a robustness checks, but I don't have that here. The most part really comes from the intraday variance. So if I go back here, I can show that maybe here. So we really just roughly like 3/4 comes from this intraday variance part, and 1/4 comes from these overnight jumps. But I don't have a table to show you that, but that's roughly what we see.
Yeah, okay, I see. Okay, well, thank you very much, Gianluca. That was a great presentation.
Thank you.